Click go now because there's a bit of a delay.
Okay.
We're live.
Hello, everyone. I'm going to hand it over to Chris. Thank you for joining us today.
Okay, welcome everyone to another live session, live from London, England. Beautiful crisp day here. We've had our rain, we've had a little bit of snow, but not much. And I'm happy to take your questions on astronomy, any subject.
All right, our first question is from Andreas, who is on with us live, who asks, something passing a big mass will follow the warped space and thus have a path that seems to be bent. What would happen if such an object stopped moving? Why should the warped space make the object fall?
That's a good question. The technical term for the warped space paths followed by objects moving under the force of gravity is a geodesic. That's how you calculate it in general relativity. And these geodesics, as implied by the question, are usually curved because mass curves space-time. So the curved path of the object is essentially, the path that it will follow based on its mass and the mass of the object that it's encountering. Obviously, if the object stopped moving, it would be subject to a simple static force. So an object next to another object will be pulled towards it essentially by Newton's law of gravity, modified if the gravity is very extreme, like with a black hole. So the geodesic really applies to a ballistic situation like a passage of a nearby star to another star or an orbit. And in that case, it does indeed describe the warping of space-time quite accurately. It's, of course, a very subtle effect. So although we talk about this for the Earth going around the sun or the star going around another star or all stars going around the center of the Milky Way, these space-time distortions are quite subtle. Ready for the next question? Okay, ready for the next question.
Oh, I'm sorry about that. I forgot to unmute my microphone. So the next question is from a live viewer who asks, when a supernova or an explosion occurs in space, what stops the matter from moving continuously through the vacuum of space? How can we see planetary nebulas and not just empty space?
You're going to have to repeat the question because you cut out for about 5 seconds in the middle of it.
Okay, I'm sorry about that. So the question is, when a supernova or another explosion occurs in space, what stops the matter from moving continuously through the vacuum of space? How can we see planetary nebulas and not just empty space?
So when a supernova happens, or planetary nebula, any of these explosive ejections of envelopes of stars, what you're seeing is the temperature of the gas. It basically shines due to its very high temperature. When it has temperatures of thousands or tens of thousands of Kelvin, the gas is ionized, and the excitation of those atoms leads to spectral lines, the kinds that we see with optical spectroscopy. When the gas is heated much more than that, is very highly ionized and even hotter, like hundreds of thousands or millions of Kelvin, then we see the radiation of those atoms or molecules as X-rays. And planetary nebula and supernovae shine both in terms of spectral lines from more modest temperatures and in terms of X-rays from high energy radiation. And even though it is an almost perfect vacuum, the sheer temperature of that outflowing gas, its energy, is what leads to the emission. So it doesn't really matter what the medium is. Now, if there is a medium that it's expanding into, then the outflowing gas will plow into that external medium, even if it's quite diffuse, and that will create shock waves. And those shock waves create enormous temperatures of millions or tens of millions of Kelvin, and that's probably the brightest form of X-rays you can see. So when you look at something like the Crab Nebula, which is a 1,000-year-old envelope of a supernova that went off in a millennium ago, most of that heated gas, those filamentary concentric patterns around the central star, a dead star, are actually representing material that plowed into a surrounding medium and heated up to X-ray. I'm ready for the next question.
All right. Our next question is, From Karen, who asks, I was wondering if dark energy interacts with any forces.
So dark energy, just as an aside, there's a lot of tapping noise. That's the signature we have of dark energy. So dark energy is a big enigma in astrophysics and in physics because we don't know what the physical means is or the mechanism of this accelerating expansion of space-time. And so we're left speculating. There are probably hundreds of theoretical papers a year written about dark energy, what it might be, the particle nature of it, what it has to do with quantum mechanics, what it has to do with string theory, what it has to do with the birth of the universe. And it's just a huge amount of speculation because we know so little about it. We do know, though, in the present universe, that the amount of dark energy overcomes the amount of matter, dark matter, which is decelerating the expansion by a factor of 2. So it is the dominant component of the universe. Ready for the next question?
All right, Chris, so unfortunately, our live stream started late. Vicki, did we start in the middle of a question?
Yeah.
Okay, so we are going to go back to the first question. I apologize, Chris. We've been having some technical difficulties. So
Okay.
I'm going to go back to the first question. I'm going to re-ask it, and we'll go through that one more time. So the question was, if you recall, was something passing a big mass will follow the warped space and thus have a path that seems to be bent. What would happen if such an object stopped moving? Why should the warped space make the object fall?
So it's a good question. The warped space that's referred to is called a geodesic in general relativity. A geodesic is the curved path, which is basically a minimum energy path in the general relativity theory, which defines the warped space-time around any gravitating object. And so this is true of the moon orbiting the Earth orbiting the sun, two stars orbiting each other. It's a very subtle distortion of space-time. If an object, and it's based on ballistics, so when objects are orbiting each other, they obviously have a particular orbital velocity. If you flew by an object in space, a black hole or a planet or a star, similarly, your path would be warped along a geodesic based on the mass of the two objects. If you were stationary at some distance from another object, then the force of gravity would in first instance just be the Newtonian force. And obviously, with two objects stationary, they move directly towards each other. And that Newtonian calculation would only be modified slightly by general relativity if the objects were very dense and massive, or the distance between them was very small. So the geodesic is a ballistic thing. It refers to objects moving. If the objects are stationary, then there is a simple force calculation between them, and they obviously move directly towards each other. Ready for the next question?
All right, and we'll go back again to one of the questions that the live session didn't pick up, which is the question about supernova and supernova explosions. And so Miguel asks, when a supernova or an explosion occurs in space, what stops the matter from moving continuously through the vacuum of space, and how can we see planetary nebulas and not just empty space?
When a supernova or a planetary nebula, both of which are envelopes of dead or dying stars expanding into space, I mean, it is essentially expanding into almost perfect vacuum. The space between stars is an incredibly good vacuum, about 1 atom or hydrogen molecule, proton basically, per 10 cubic meters. And we see the gas not because of the nature of the medium it travels through, but because the gas itself is incredibly hot, heated by the explosion or the initial impulse. If the gas has temperatures of tens of thousands of Kelvin, it will excite its electrons and you will see spectral lines, and so it will have the pretty colors of nebulae. If the acceleration or the energy in the gas is even larger, creating temperatures of hundreds of thousands or millions of Kelvin, which definitely happens in a supernova, if not a planetary nebula, then that gas will glow in X-rays, like any gas would at that temperature. It's a plasma, actually. Now, the vacuum of space is not, of course, perfect, and so over some large distance and after some time, this gas that's moving outward from the dead star will sweep up the material around it, compressing it and actually creating a shock wave. And the shock wave, when the outflowing gas impinges on a very diffuse medium, but gradually plows into it and heats it, creates probably the most intense X-ray emission in a supernova. So if you look at the Crab Nebula, there are some beautiful X-ray pictures of that. The filamentary gas that's seen glowing in X-rays in sort of roughly concentric circles around the central dead star is a representation of what happened when that outflowing gas plowed into a surrounding medium. The Crab Nebula is a 1,000-year-old explosion, so this gas has been traveling at near relativistic speeds for almost a millennium. Ready for the next question? Ready for the next question?
I'm sorry, this microphone. The next question is from Ilsa Martin, who asks, have false color images, like in X-ray, produced valuable new insights or just prettier pictures?
I would say for the most part, false color is just pretty pictures because the phrase sort of gives it away. It is false color. We obviously cannot see directly or experience radio waves or X-rays or gamma rays or infrared radiation. And so to visually represent this, we have to convert a map of intensity in an invisible wavelength like X-rays or radio waves into colors. And typically the way that's done is, as with the visible spectrum, the higher energies are represented as blue and the lower energies are represented as red, which would be true for visible light. So it's a mapping of energy or wavelength into spectral color in the visible range. And it's false because the energies involved when it's beyond the visible spectrum are, of course, either much lower than visible light or much higher than visible light. And in that sense, it's false. What it is useful, however, for is for elucidating the structure and nature of the phenomenon that lead to that emission. When you render an X-ray or radio map with high resolution and turn it into an optical image, map it into optical wavelengths or visible colors, you see the detailed structure, and it's helpful for diagnosing what's going on. So astronomers use these false color maps as guides to the physics of what's going on, but they don't extract numerical information from them because it's a false mapping. Ready for the next question?
Okay, the next question is from Akash, who asks, how technically correct is it to say life cycle of a star? How much of the nebulous gases from the end of a star's life actually form a new star on average?
So a life cycle is a useful term. So to make an average, which is a useful thing to do because stars are very different, roughly a third of the mass of any star will be recycled into the interstellar medium. That, for example, is about the number that will happen for the sun. The sun will eventually eject some of its material, about a third, into a planetary nebula envelope, and the remainder of the star, some more mass will have been lost very slowly over a longer period of time. About 2/3 or 60% will go into a white dwarf. And so that's the fate of the sun. And that's typical. The most massive stars actually lose a larger fraction of their total mass into ejected envelopes. For example, a supernova is the violent ejection of possibly 2/3, 3/4, or even 80% or more of the star's mass into the space between stars. But a good average is about a third. Ready for the next question?
Okay, our next question is from a live viewer who asks, I would like to know if dark matter can form stars or black holes.
Yeah, an interesting question. As far as we know, no. Dark matter is defined by the fact that it doesn't emit light. We can't see it. And that means that its interactions by the electromagnetic force or the weak force are weak. Essentially, it only has gravity. And because it only has gravity, it of course does clump. And so dark matter is not uniformly distributed in space. Even on the largest scales between galaxies or within a cluster of galaxies, dark matter is concentrated towards the center of the cluster or the center of the galaxy. But it spreads out over a much larger region than the visible mass. So dark matter of itself can cluster, can clump, because it has the force of gravity, but it can never create its own stars. It's made of a particle, we think, a weakly interacting massive particle, or WIMP, as the acronym for that, that has not yet been seen in accelerators. And so we don't actually know in physics terms what that particle is. But either way, the particles that we think dark matter is made of are not the kind of things that can form stars themselves. Ready for the next question?
All right, our next question from a live viewer is from Sulley V Live, who asks, if the universe is expanding increasingly rapidly and in all directions, why do galaxies collide with each other?
It's a good question. If everything was sort of uniform and evenly spaced, then the galaxies would just be markers of expanding space-time and they would all just sail apart. But of course, there is inhomogeneity in the universe. This inhomogeneity, which means that density early in the universe was slightly higher in one place than another place. This inhomogeneity was very small. At the time of the microwave background radiation, the variations in density from one point in space in a tiny universe to another was 1 part in 10 to the 5, very small. But gradually over time, this got amplified. Gravitational perturbations, as they're called, would gradually amplify this, and eventually there were quite large variations in density from one region to another. Now what this means is that galaxy formation, and to use astronomers' term for it, is biased. That there are some parts of the universe where the mean density was higher early on, where more galaxies formed than other parts of the universe. And because those galaxies form at a higher density and concentration, their gravity between each other is stronger. And so they can be bound into a cluster and occasionally into a supercluster. So it's quite routine in the universe, even though the overall space-time is expanding, to have significant concentrations of matter, galaxies in pairs, groups, clusters, or even superclusters, where those groupings are bound by their internal gravity and are not participating in the cosmic expansion. We can even have a situation such as with the Milky Way and Andromeda, M31, where for the first 2/3 of the universe, the Milky Way and M31 were moving away from each other, as the Hubble expansion would indicate, but they were close enough and their mutual gravity was strong enough that they gradually started to approach each other. And now we know that the two galaxies will collide in about 4 or 5 billion years. Ready for the next question?
Okay, our next question is from Johan, who is from Colombia, who asks, what's the difference between redshift and Doppler effect in order to observe stars?
So for stars, we can generally say there is no difference, really, because stars in the Milky Way, for example, exist in a bound system. So the stars in our galaxy are either orbiting the center of our galaxy on circular orbits, like the Sun is with all the other stars in the Milky Way disk, or they're orbiting in looping elliptical orbits around the galaxy center, the way the stars in the halo are. Because they're all part of some large system, we can think of their motions in relative terms. And so there's no distinction between Doppler shift and redshift. In other words, we're not looking at a cosmological redshift here. We're just looking at a redshift, which is the fractional change in the wavelength of light caused by relative motion. So these are the same things. However, when we start to talk about other galaxies, we're no longer talking about a Doppler shift because the reference frame is the expanding space-time of the universe itself. So we make this distinction between Doppler shift and redshift for cosmological situations, but we don't make it for a smaller scale situation such as within the solar system or within the galaxy. Ready for the next question?
Our next question is from Miguel, who asks, what philosophical implications come from getting to understand completely how the universe works in its macroscopic and microscopic properties?
That's a big question, and cosmology does shade into philosophy at some level. I think the implications for understanding the birth, current situation, and fate of the universe are enormous and profound because this is a situation where one species on one planet in one part of a vast universe, situated at a particular point in time, far removed from the birth of the universe, have been able, we think, to figure out the entire system of which they're a part and its chronology from the past through to the future. That's an amazing achievement, and it is worthy of consideration in terms of philosophy as well, of how we know our place in space and time. Now, it doesn't mean we've answered all the questions. So in terms of physics or philosophy, there's still some profound questions remaining, the biggest, of course, of which is what caused the Big Bang and why does the universe exist at all? And that now is a question that has moved beyond physics into philosophy, and one which we currently can't answer. Ready for the next question.
All right, our next question is from Siddharth, who's on with us live, who asks, if dark energy is making our universe expand, then does this mean the Big Crunch theory is false?
We think so. So the Big Crunch theory has actually been out of favor for almost 50 years. So before dark energy was found, before the accelerating expansion was measured in the mid-1990s, the only thing that could have overcome the expansion of the universe was mass, enough mass to overcome the Hubble expansion and lead to eventual contraction. But the amount of matter that was found through the 1970s, including the dark matter, because dark matter was on the table by the 1970s, was way insufficient to overcome the expansion. So even before, 2 decades before dark energy was on the table, there was insufficient mass in the universe, including the dark matter, to overcome the expansion. And so the Big Crunch idea has really not been relevant in cosmology for almost half a century. Ready for the next question.
All right, the next question is about supernova, and it's from Ayad Ali, who asks, how far would a supernova have to be from us to make some real damage here on Earth?
So the best calculations on this, supernovae, of course, there are different kinds of supernovae. They have different energies. The type 1A supernovae, the type that we use for measuring distances in the far-off universe, have all roughly the same energy, so that's the one people standardize on. These are binary system supernovae, where one of the stars becomes massive enough to go as a supernova. The type 2s are individual massive stars, and they can have larger luminosities. But for a typical supernova, 10 light years is about the boundary within which a significant damage would be done to the Earth from the explosion itself. And mostly it would be from the high energy radiation that came from the explosion, not really from the expanding shell of gas, although that could cause a problem with our atmosphere. The high energy radiation would potentially destroy the ozone layer and therefore lead to a spike in the mutation rates for all terrestrial life, all life on the surface. Life in the ocean, I guess, would be immune from this. So the damage from a supernova is really caused by its high energy radiation, its effect on the biosphere, not really by direct ballistic impact of the expanding gas on the Earth's atmosphere. By the time, even at 10 light years away, that gas is diffused over such a large volume that it has a very limited push on the Earth's atmosphere. Ready for the next question.
Our next question is from Angelo, who asks, how or does dark matter seed the universe formation process on a macro scale?
So dark matter is an ingredient in the standard cosmology, and it's there in an abundance that's about 6 times that of normal or baryonic matter, the stuff that we're made of. And when the best we understand this is by using a computer simulation, supercomputer simulation. So you can put dark matter and normal matter into a simulation and let the Big Bang go and watch matter expand and radiate and lose energy. And eventually you start to get clustering. Now what happens, of course, is that the dark matter is only feeling gravity. The normal matter is feeling electromagnetic radiation. And so for the first 10,000 years of the universe is dominated by radiation. And this impacts the ability of normal matter to cluster. And so baryonic matter sort of lags behind dark matter in terms of clustering and clumping for the first 10,000 or so years. Eventually the normal matter catches up, and so in lockstep, dark matter and normal matter start to clump. And at the point where the deviations in density approach 100%, so one region may be twice as dense as a neighboring region, then it goes nonlinear, to use a physics term, and that acceleration or that process of clumping accelerates, and at that point you start to form galaxies. But even so, the dark matter and the normal matter behave differently. The baryonic or normal matter is able to lose energy by dissipation processes, because again, it interacts with radiation and emits radiation. And so the normal matter clumps more efficiently to the center of the more diffuse wells of dark matter. And so we get the situation over time, taking several hundred million years for this to happen first, of small concentrated lumps of visible baryonic material turned into stars, a galaxy essentially, embedded in a much larger and more diffuse dark matter halo. Ready for the next question?
All right, the next question is from Karen, who asks, what is a Higgs field?
The Higgs field is the field. A field in physics is, of course, a situation where even in a vacuum, there's some potential for energy to be transferred or transmitted or work to be done. So it's the potential for something to happen, for energy to change. The Higgs field is a field imputed to give mass to normal particles. So it was a mystery for some period of time in the standard model of particle physics why the particles had the masses they do. Why, for example, is the proton and the neutron almost 2,000 times more massive than the electron? Now, we don't exactly know how to explain the various mass ratios of fundamental particles, but the single mechanism by which they get mass is called the Higgs field. So if you just hypothesize a field that permeates space, and by the interactions of different particles with that field, they attain the property of mass, which we can think of in terms of their inertia, their resistance to any change in their motion. This mechanism was proposed in the 1960s and developed more firmly in the 1970s. And of course, the Higgs particle, the carrier of this field, was detected in CERN in 2013, led to the award of a Nobel Prize a few years later. Ready for the next question?
All right, the next question is from Pikaraza, who asks, does gravity act instantaneously or is it transmitted at the speed of light?
So in the theory of gravity, general relativity, the theory of relativity that explains gravity as well as we understand it, gravity does propagate with the speed of light. If anything were to propagate instantly, that's an acausal, that essentially breaks causality. So to preserve causality in physical theory, the speed of light is the absolute limit. That's what special relativity said, and general relativity agrees in that regard. So in the hypothetical case of an exchange particle that carries the force of gravity, the standard model of particle physics called the graviton, that graviton propagates at the speed of light. Have we ever been able to show that gravity propagates at the speed of light? No. Obviously, if you have mass, it's very hard to just extinguish mass and switch off gravity and then see what happens. So this is a very hard experiment to do in the universe itself. Physicists have tried to create very imaginative ways of indirectly measuring the rate at which gravity propagates, but have been unable to do so. So this is an experiment that has not yet been carried out. However, it is important to know that with the detection of gravitational waves, which is a related prediction of the general theory of relativity, we do know that gravitational waves, perturbations in space-time caused by change in mass, do propagate at the speed of light. LIGO, its various detections, and all the work done since then have confirmed that. Ready for the next question? Ready for the next question.
Oops, my apologies again. The next question is from Bhaskar, who asks, why are we 13 billion years away from the starting point of the Big Bang that light can't even reach us yet? And how has matter reached this far?
Well, the interesting and slightly confusing thing about cosmology is that the Big Bang was not really a place. It was a time. The Big Bang was everywhere, and the universe we live in is everywhere. So although we see galaxies moving away from us and we can project back in time to a point in which all those galaxies were on top of us, every other place in space can do the same thing. And following the logic, all places in space that are now separated were once one place, and that place was the Big Bang. So it's a kind of confusing situation. It's really confusing because we tend to think of analogies in our head, and so we imagine a balloon or we imagine a volume expanding. And this is a three-dimensional curved space-time expanding. So every part of the space, the expanding space, sees essentially the same thing. That's called the cosmological principle. So there's no special position for our location and no special perspective on what happened from our location. Ready for the next question?
Okay, the next question is from Kushal, who asks, what causes variability in T Tauri stars?
In T Tauri stars and in the very many other kinds of variable stars, there's 50 or 60 different types of variable stars. These are typically caused by energy instabilities in the mechanism that leads to energy release. They're typically advanced stages of stellar evolution where the sort of routine, humdrum, and very level fusion rate that we experience in the sun as it turns hydrogen into helium start to become more unstable. When there's any change in the energy production in a massive or evolved star, then that change in energy production will cause, if the energy production goes down, then the temperature will go down and the star will puff in a little or contract slightly. As it contracts, the gas heats up, and so that heats up the fusion rate, and the fusion rate increases, and that puffs the star back out again. So you can set up an oscillatory mechanism here, like thermostatically controlled essentially, by the expansion and contraction of an envelope, an outer part of a star, and its effect on the fusion rate. And that's really what's happening in most variable stars. And it continues in that way just for some phase of the star's life until the fundamental energy production mechanism changes, and then the star has to do a more dramatic reconfiguration, or sometimes at the end of its life it just dies and has an explosive event. Ready for the next question?
The next question is from Spy332, who's on with us live, who asks, what is your opinion, or are there new insights regarding the Oumuamua asteroid's weird orbit and movement?
There's no verdict on that, actually. There's also not a lot of new data. So Oumuamua is this extraordinarily elongated asteroid, by far the most elongated asteroid we've ever seen. Most asteroids are potato-shaped or slightly elongated or elliptical. They're not extreme in their shape. When people see asteroids with this structure, they tend to think they resulted from a collision, a merger or partial melting and a merger of different objects. And that also can be used to explain an unusual orbit, because when objects collide, the orbit of the product can change substantially from the two initial pieces. And so that is still a speculation for Oumuamua, but the truth is it's a one-off. We would need a set of these objects to form a real hypothesis as to how something of this strange shape formed. It's, at the moment, a unique object and very interesting. Ready for the next question?
All right, the next question is from Kushal, who asks, with respect to what do we measure the expansion velocity of space-time?
Slightly infuriatingly, the answer is with itself. There is no reference or external reference for the expansion of space-time. The universe is described as an expanding space-time, and that description in general relativity requires no external medium. It requires no frame of reference beyond the space-time described by the theory itself. That sounds like a very Zen-like way to describe it, but that's literally what the theory says. And so there's no implied external situation or external reality to the space-time that we occupy. Ready for the next question?
All right, the next question is from Aditya, who asks, we are being told that the universe is expanding, but we aren't told what exactly we are expanding into.
So this is related to the last question, and the answer is we're not expanding into anything because the theory does not describe a situation where that is a required concept. Again, general relativity is a description of expanding space-time and how the contents might behave, and requires no external reference. And so, although it's a very tempting psychological intuitive crutch to think of expansion into another medium, it's not part of the theory, it's not required, it's an unnecessary hypothesis, essentially. Everything we know, everything we can measure, everything we can explain in the theory of general relativity is embedded or accommodated by the space-time itself and its expansion and event and evolution. And so no other construct is necessary. Ready for the next question?
Okay, the next question is from Pravya, who asks, Sir, How did we know that the sun is larger than the moon before we sent telescopes into outer space?
Well, the first speculation that the sun was larger than the moon and larger than the earth was actually done by the ancient Greeks. So the Greeks developed some interesting ideas of astronomy, obviously long before the telescope. Some of this work done 1,500 years before the telescope. And they used essentially ideas of geometry. So the classic thought experiment, because you can do these calculations and the measurements are actually quite simple, was done in, I think, the 2nd or 3rd century BC. And who actually did it? Aristarchus did some of it, but there's a little argument as to who all was involved in this. Used the fact of eclipses. First of all, it used the fact that the moon, during a lunar eclipse, we see the shadow, the curved shadow of the Earth on the moon, and that tells you the relative size. If you know the illumination geometry of the Earth, Sun, and Moon in an eclipse situation, then that tells you how much smaller the moon is than the Earth. To do the Earth, Sun, Moon as a triple system, you use the time between a first quarter moon and a third quarter moon, when the moon has traveled 180 degrees relative to the Earth with respect to the sun. And because that angle is actually slightly less than 180 degrees, you can measure a similar triangle. And that similar triangle gives you the relative Earth-Moon size and Sun-Moon size, and allows you to say that both the Earth is larger than the Moon and the Sun is larger than the Earth. So people did this long before the telescope, and those people who did this calculation, it was rough, it was not a very accurate answer, used therefore a logic that if it made no sense at all for the bigger thing to go around the smaller thing. And so this was an argument long ago, way before Copernicus, for a heliocentric cosmology. Ready for the next question.
Okay, our next question is from a live viewer, Chandran, who asks, high velocity stars are measured to travel faster than the speed of light. Does this contradict Einstein's theory?
I think I'll correct the questioner, because not to my knowledge does any star travel faster than the speed of light. We would not see such objects, in fact, and that also goes against physics. High velocity stars, however, is a phenomenon. So there are high velocity stars that we found leaving the Milky Way. Sometimes we observe them within the Milky Way, but they have more than an escape velocity from the Milky Way. And so we know these stars are somehow unbound. We think sometimes these stars were caused by close interactions in a binary system between a much more massive companion and a small object, where the small object is kicked out with very high speed. So there are indeed high velocity stars seen in our galaxy, which are moving so fast they must escape the Milky Way system, but they're not traveling faster than light. In fact, they're not even relativistic, which is just to say they're not within 10% of the speed of light. Ready for the next question.
All right, our next question is from Anita, who's on with us live, who asks, in A Brief History of Time, Stephen Hawking said that the biggest issue in astronomy was how to unite quantum mechanics with the theory of relativity. What are the most recent achievements in that area?
He was right then, and it's still right now, even though he's been lost to us for a year or so. This is the big unachieved agenda of physics, to unite the general theory of relativity, our theory of gravity on large scales, with the very successful theory of quantum mechanics on small scales. So these are two very successful theories in their own regime, which do not play well together, if you like, in terms of the mathematics. There are essentially no brand new efforts in this regard. String theory was the relatively new agenda on the table, put in the last 2 decades on the table. So people have been trying to use string theory as a way of reconciling general relativity and quantum theory, with some small successes, but with no large success. Some people think string theory is maybe even played out, that it's not been able to make enough unique predictions that it's worth all the effort, and especially all the talented young physicists that have devoted their time to it. So that was the new ingredient on the table. Quantizing general relativity has proved to be an extremely difficult thing to do. You essentially have to go back to scratch in your gravity theory to develop a quantized theory of gravity. You can't alter or modify general relativity the way Einstein configured it. So this is an extremely difficult thing to do, and no one has succeeded. And in fact, the way forward is not even clear at this moment. Ready for the next question.
Okay, our next question is from Preston, who's on with us live, who asks, do you think an idea like quantum entanglement could have macroscopic influences? For example, could a group of entangled particles provide instantaneous information transfer on an astronomical scale?
That's a fascinating question, and people are trying to find the answer to that. So quantum entanglement for people who haven't been keeping up, has already moved out of the lab. So entangled quantum states have now been demonstrated on intercontinental scales between a lab, I think, in the Canary Islands and one in the main continent of Europe, so thousands of kilometers. An extraordinary success. So quantum entanglement is a highly macroscopic phenomenon that works on essentially planet-sized scales. Whether it also works on star and galaxy-sized scales is completely unknown at this point. And it's also hard to really understand how to do an experiment, because these are lab experiments essentially, where you use partially silvered mirrors to essentially split photons and send them along two different paths and then recombine them by interference. We don't know how to do that as a lab experiment beyond the Earth, and so there's no real way to test entanglement beyond the Earth at the moment. Ready for the next question.
The next question is from a live participant who asks, so is there reason to believe that there are clumps of dark matter out there, for example, planets? We talked about stars and galaxies earlier, but could there be clumps of dark matter in any form?
It's an interesting supposition. So generally no, because if you do a computer simulation where you put dark matter in and evolve a universe, you can watch the way dark matter clusters by gravity, because it does feel gravity, and it produces rather gentle concentrations of dark matter that gradually grow over time. And these are basically the huge halos that galaxies, the visible parts of galaxies, are embedded in, and the sort of undulating density of dark matter in intergalactic space. So generally no, because dark matter clusters so slowly and is unmediated by any other force like electromagnetic interactions that you don't tend to get lumps of dark matter. But in the centers of some high density situations, like a cluster of galaxies or a very massive galaxy, the dark matter does have quite a high density. Now, completely separate from this, and not knowing what the dark matter particle is, people have speculated that the dark matter particle might form concentrations early in the universe, when the universe was very hot and dense, nuggets of dark matter, if you like. That depends on dark matter being particles that are, to be honest, not the best candidates for dark matter at the moment. So at the level of pure speculation, yes, because we don't know what the particle nature of dark matter is, some of the particle candidates are candidates that could clump early in the universe, although not more recently. Ready for the next question.
All right, thank you, Chris. The next question is from Pravya, who asks, why does the moon orbit the Earth when it might as well only orbit the sun? Why don't other planets orbit each other? Are they too fast or not close enough, or both?
So those situations are seen. So planets do orbit each other in other situations. There's been a question in the research literature recently of, can moons have moons? That's a theoretical question and an empirical question subject to observation. And there's no theoretical reason why moons can't have moons and planets can have planets that orbit them. And it becomes almost semantic at some level whether a moon going around a planet is big enough to be called a planet itself. As we know, in the solar system, the largest moons are bigger than Mercury and Pluto. Pluto is not a planet, but bigger than Mercury. So moons can definitely be as large as planets. But in general, for the moon and the Earth, that we have a clear answer to the question, because we pretty much know that the moon is formed by the impact of a Mars-sized planetesimal in the very early solar system, that while the Earth was still molten, splashed off a significant fraction of its mass into an orbit around it. That orbit gradually circularized and formed the moon. And so because the moon formed from a collision and that material never was sent to an escape velocity, the moon is a bound object of the Earth, and that's why the formation happened that way, and that's why the orbit is the way we see it now. Ready for the next question?
All right, our next question is from Siddharth, who asks, humans are planning to go to Mars in 2022 or so. To do this, they have to pass through the Van Allen radiation belt. How can we shield ourselves against radiation while going to the red planet? And just, I guess, in more general terms, can you talk about what are the dangers of traveling to Mars?
The dangers are significant, and they've been sort of measured or guessed or extrapolated. Yes, as soon as you leave the protective radiation belts of the Earth that shield us from high-energy particles and cosmic rays coming from the sun mostly, but also from interstellar space, then you're in a high-exposure regime. So in simple terms, assuming a 6-month journey to Mars, a couple of weeks or maybe a month there and then 6 months back, the astronauts who make that journey will have roughly 2 or 3 times what would be a normal lifetime exposure to radiation on the Earth. Now that sounds really bad, to get 2 or 3 times lifetime dose in 1 year of your life, but actually the incremental increase in cancer risk from that is only 6 or 7%. So this is not as dramatic as it sounds. Worse will be when we have Mars colonists, because Mars, of course, is not shielded from this radiation either. So unless the Mars colonists were in really hardened, thick, terraformed structures that shielded from all radiation, those Martian colonists would very quickly get an awful, damaging lot of radiation. But just for one trip, it's totally survivable. Ready for the next question?
All right, our next question is, what would be more disastrous? And I guess we'll have to speculate a little bit about the location, but what's more disastrous, a black hole or a supermassive star? So I guess maybe what's more dangerous in general for humans?
Well, it depends on proximity. A supermassive star in the end is more dangerous because the supermassive star is one that, if it's by supermassive, I assume you're talking about the most massive stars that nature makes, which is 150 times the mass of the sun. Well, those stars have very short lives of fusing hydrogen into helium, and they die catastrophically as supernovae. So the most massive stars that nature can make are, of course, extremely dangerous because they have a short life and then they die explosively. So being anywhere near, within 5, 10, 15 light years of such a star would be extremely dangerous. In a sense, a black hole is less dangerous because unless you're really close to it, the gravity from a black hole is very close to what you would calculate with a Newtonian calculation. And if the black hole is just the mass of the sun or a few times the mass of the sun, it doesn't have an extreme amount of gravity in the first place. So as long as you keep your distance, the black hole is actually safer than the supermassive star. Ready for the next question?
Okay, we have this one more question. I believe this will be the last one for today. This is from John, who asks, what can we learn from astronomy or astrophysics that can teach us about climate change, but then also that might help convince people or naysayers that climate change is real and needs to be addressed?
It's a good question. I think what we really learn from astronomy that affects the arguments about climate change is, since the sun obviously controls our environment, it controls life on Earth, and it has some effect on climate. What astronomers can do is be as clear as possible about what the impact of the sun is on our climate from year to year or decade to decade, because some people who deny the fact that the Earth is warming have pointed to changes in the sun, for example, the solar magnetic cycle, the fact that there was a little ice age a few hundred years ago when the sun had a long sunspot minimum, have used such arguments to say that really what's happening on the Earth right now is controlled by the sun and not by our own actions and carbon dioxide emissions. And I think astronomy and astrophysics can clearly rebut that. So probably the biggest thing that astronomers can do is to just be very clear about the arguments and what we know about the sun and its effect on the Earth to show that the sun cannot explain what's happening on our planet in the last century in particular, when the surface temperatures and ocean temperatures have risen quite dramatically. So good range of questions from cosmology to climate science. Thanks for participating, and we'll be back with you again in a couple of weeks. And thanks to Vicky, Alexander, and Matthew for facilitating this session. That's all for today. Bye.